Hello students, welcome to my channel. In this class, I am going to teach you fundamental theorem on arithmetic, particularly basing on prime numbers. So let us start the topic. Fundamental theorem on arithmetic. The statement of the theorem is every positive integer n greater than 1 can be expressed as the product of prime factors uniquely. So proof. Let n be a positive integer. So now add n greater than 1. So n be a positive integer, n greater than 1. Now two cases arises. Case 1. Let n be a prime number. N be a prime number. So then we have nothing to do. Then we have nothing to prove. Because n is itself a prime number, so it cannot be factored further. Case 2. Let n be a composite number. Then we can write n is equal to P1N1, where P1 is a prime number. P1 is a prime number. Now N1, which is a positive integer, may be prime, may not be. If N1 is a prime number, then n is expressed as product of primes. But if N1 is a composite number, then we can write N1 is equal to P2N2, where P2 is a prime number. P2 is a prime number. Then from equation 1, get n is equal to P1, P2, and if N2 is a prime number, then N is expressed as product of our primes. But if N2 is a composite number, but if N2 is a composite number, then we can write N2 is equal to P3 N3. Then from equation 3 we get N is equal to P1, P2, P3, and 3. If N3 is a prime number, then N is expressed as a product of primes. But if N is a composite number, then we can write N3 is equal to P4 N4. Now, if N4 is a prime number, then N is expressed as product of primes. But if N4 is a composite number, then we can write N4 is equal to P5 N5. And this process will continue and this process will continue. And this process will continue. But the process cannot continue infinitely, as n is a finite positive integer. Then clearly after finite number of steps we get n is equal to P1 into P2 into P3 into P4 into the dot Pn. Here P1, P2, P3, Pn are prime numbers, and P1 less than P2 less than P3 dot 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 less than Pn. N greater than N1, greater than N2, greater than dot dot dot. So where P1, P2, P3, Pn are prime numbers, P1 less than P2 less than P3 dot dot Pn, and N greater than N1, greater than N2, greater than dot dot dot. So this shows that the positive integer n greater than 1 can be expressed as a product of a primes. Now to prove this expression as product of primes is unique. Now to prove the expression as a product of primes is unique. If possible, let we have two expressions for n. If possible, let n can be expressed as n is equal to P1, P2, P3, P r is equal to Q1, Q2, Q3, Qs, where R less than S. So this is the expression. Now we are having two expressions for n as a product of primes where P1, P2, P3, Pr are prime numbers and Q1, Q2, Q3 are Qs are prime numbers. Where P1, P2, Pr and Q1, Q2, Qs are prime factors. Now P1 divides Q1, Q2, Q1, Q2, Qs. But here P1 is prime, Q1, Q2, Qs prime. So this implies P1 must be equal to Qk where 1 less or equal to K less or equal to S. Next. Let us rearrange Q1, Q2, Qs in such a way that P1 is equal to Q2. Then we get P1 is equal to Q1. Then we get P2, P3, Pr is equal to Q2, Q3, Qs. In a similar manner, let us take P2 is equal to Q3. Then we get the reduced equations P3 Pr is equal to Q3 Qs. After finite steps, repeating this process here, that means R number of times, we get 1 is equal to Q R plus 1, Q R plus 2 up to Qs as is greater than R. But QR plus 1, QR plus 2, QR plus S are prime numbers. But QR plus 1, QR plus 2, QS are primes. So the above equation is not possible. So it means we get R is equal to S and P1 is equal to Q1, P2 is equal to Q2 and PR is equal to QR. So this shows that the expression for n as a product of primes is unique. So the theorem is proved. Next, let us solve a problem. If n is a positive integer and n greater than 1, such that n is equal to a to the power p, b to the power q, c to the power r, where a, b, c are distinct primes, then number of divisors of n is equal to p plus 1, q plus 1, r plus 1. Sum of divisors of n is equal to a to the power p plus 1 minus 1 by a minus 1 into b to the power q plus 1 minus 1 by b minus 1 c to the power r plus 1 minus 1 by c minus 1. So with this information, let us solve a problem. Find the number of divisors and a sum of divisors of 144. Find the number of divisors and sum of divisors of 144. Solution 144. So let us divide it by 2. 72. Divide by 2. 36. Next divide by 2. then divide by 2, and this is 3 into 3. So we get 144 is equal to 2 to the power 4, 3 square. Then the required number of divisors is equal to 4 plus 1 into 2 plus 1. 5 into 3 is equal to 15. It means there are 15 divisors exist for 144. Then add the required sum of divisors equals to 2 to the power 4 plus 1 minus 1 by 2 minus 1 into 3 to the power 2 plus 1 minus 1 by 3 minus 1, which is equals to 2 to the power 5 minus 1 by 1 to 3 to the power 3 minus 1 by 2. So this is equals to again 32 minus 1 by 1, 27 minus 1 by 2. This is 31 and this is 13. So let us multiply. So it is equals to 403. So we get the number of divisors and the sum of divisors of 134. So the problem is now solved. The topic for the today class is completed. I shall meet you with a new topic in my next class. Till then, goodbye.